Hello. In the previous video, we learned that when nucleons come together to bind into a nucleus, energy is released to the surrounding. As a result, the system has lost energy. According to the mass energy equivalence principle, the loss of energy must come with a corresponding decrease in mass of the system. And this decrease in mass is called the mass defect. So that's where we ended in the last video. Let's continue from here. Now the mass defect is a mass, right? It's measured in kilograms. It's not energy. So according to E is equals to mc squared, if you take the mass defect, multiply it with c squared, c is of course the speed of light, you will get an energy, and the energy is called the binding energy. So numerically, binding energy is very straightforward, right? You just take the mass defect and multiply it with c squared. But what is the physical meaning of binding energy? Well, you can think of it as the energy that's released to the surrounding when a nucleus is formed. So that's the first interpretation of binding energy, is the energy released during the process of binding the nucleons to form a nucleus. But you can always reverse the process, right? If you want to break this nucleus into its original nucleons, you have to put back the energy that's been released, right? So you've got to put back the energy in order to split the nucleus into its original nucleons. So that's the second interpretation to binding energy, is the energy required to unbind the nucleus into its original nucleons. Now, I'm not sure whether when we decided to call this thing the binding energy, we meant the energy released or the energy that must be put back in. But I guess it doesn't matter, huh? Numerically, they are the same. And conceptually, I think we got to be agile. When somebody uses the term binding energy, that person may have in mind energy released or the energy that must be supplied. I guess you just have to base it on the context. Okay, so as I said, every nucleus will have a mass defect, but usually what is more useful is the binding energy. So you can see here, as the nucleus gets larger, A represents the nucleon number, yeah? So as the nucleus gets larger and larger, the binding energy also becomes larger and larger. So does it mean uranium-238 is the strongest nucleus or something like that? Not really, yeah? 1800 mega electron volt just means that if you want to break down uranium-238 completely back to its original 238 protons and neutrons, 1800 mega electron volts of energy is required. But then if you want to break a uranium-238 nucleus, you don't have to break it down completely, right? Even if you take out just one neutron or one proton, it's no longer uranium-238. So in that sense, binding energy does not reflect the stability of any nucleus. If you want a measure of stability, the binding energy per nucleon is a more representative number. So this symbol here is just the binding energy divided by the number of nucleons. So Be/A. Now you see that binding energy per nucleon doesn't keep increasing. That's unlike the binding energy. The binding energy keeps increasing. But the binding energy per nucleon kind of increase and then decrease. So why not we plot the binding energy per nucleon against the number of nucleons? And then we get this graph here. So on this side here, you have the small nuclei, right? The hydrogen, helium, lithium, nitrogen, and so on. As you go more towards the right, you go towards the bigger nuclei, krypton, the tin, and the uranium. So the trend of the binding energy per nucleon is to increase quite rapidly, but soon it kind of plateaus off, yeah? The maximum happens around here. In fact, iron-56 with a binding energy per nucleon of 8.8 mega electron volts is usually touted as the most stable nucleus. Because beyond this point, the binding energy per nucleon will start to decrease steadily. So why do we say it's the most stable? Because if you want to just plug one neutron out of iron-56, you need 8.8 mega electron volts of energy. Whereas if you want to plug one neutron or proton out of a uranium-235, you require something that's around 7.5 mega electron volts. If it takes less energy to change the composition of the nucleus, then it's a less stable nucleus, right? Now, besides showing us that iron-56 is the most stable, this chart here is actually more useful than that. If you want to find a treasure, you need a treasure map, right? So if you are looking for nuclei to harvest nuclear energy from, this chart here is kind of like the treasure map for you. Let's start with the trend for the small nuclei first. For the small nuclei, you notice that the binding energy per nucleon is rising, right? That means if I combine two hydrogen-2, for example, I can form a helium-4 nucleus, isn't it? But the helium-4 nucleus has a much higher binding energy per nucleon compared to the hydrogen-2 nucleus. See, it has gone up from about 1 mega electron volt to about 7 mega electron volt. Now you can think of the binding energy as the nuclear energy that has been cashed out, right? The nuclear energy that can be released as the nucleus is formed. So as hydrogen-2, I've only cashed out about 1 mega electron volt per nucleon. But as helium-4, I stand to cash out 7 mega electron volt of nuclear energy. That tells me that if I can get two hydrogen-2 to fuse to become a helium-4, I can get energy released through the process. This explains why scientists are always trying to study the nuclear fusion of two small nuclei, because we are looking for the energy that will be released during the nuclear fusion. So that's the trend on this side of the charge, right? The trend on the other side of the charge is the opposite. The binding energy per nucleon is decreasing. If you try to fuse these two nuclei, for example, you end up with a nucleus with about 200 nucleons, somewhere here. You end up with a nucleus with lower average binding energy than before. Not only will energy not be released in the process, you actually have to supply energy for this fusion to happen. So we are not so interested in such processes because we want the nuclei to give us energy, not the other way around. So if you are looking to harvest nuclear energy from large nuclei, what you should do is to try to split them. For example, the uranium-235, if you can split them into two nuclei, maybe one with about 100 nucleons and the other one with about 135 nucleons. So you end up with two nuclei, one sits about here and one sits about here. Both will be having a higher average binding energy than what we started out with. So what the chart is telling us is there's a possibility of cashing out additional nuclear energy if we are able to achieve the nuclear fission of a large nucleus. Okay, I hope now you understand what is the mass defect, what is the binding energy, and what is the binding energy per nucleon. And why, if you are looking to harvest nuclear energy, you should be looking to the nuclear fusion of two small nuclei or the nuclear fission of a large nucleus. Alright, that's all. Ta-ta!